We will move on to our next workshop now, that is on our mountain climate and environment impacts and changes. And our speaker for that is Dr. Chelsea Ford-Miniet, who is a research ecologist and research project leader with USDA Forest Service at the Coweta Lab. She is also the co-lead investigator for the LTER. Most recently, she served as Senior Policy Advisor for Water and Natural Resources for the Chief Scientist of USDA. Her research is centered on developing an understanding of watershed ecosystem function under changing management and climatic conditions. It contributes information readily usable by policymakers attempting to formulate effective strategies for preventing, mitigating, and adapting to the effects of climate change.
Chelsea and I just got our act together more recently, and we switched around a little bit. So I was asked to speak also on forest ecology as a forest ecologist on what we might anticipate to happen to the forests in our region. And I'm going to just talk a very short time about that, and Chelsea will definitely speak largely on the Coweta scientific research. I'll just give a short thing about this. We can't actually predict what changes are going to occur in our southern Appalachian forests. We can look at how historic environmental conditions and topography, climate, have resulted in the forests that adapted to these conditions that are here today. Then we can look at forecasts of climate and try to imagine and predict what might happen, how different forest ecosystems might change according to the changing climate conditions. There are a couple ways to do this. On one hand, we can use observations of recent decades, simple observations that we've seen. We can also look at studies that are now being undertaken in forests, trying to measure changes that are happening now. And the other thing is we can also use computer modeling. I'm not an expert on computer modeling, but that is a very important way to look at what might happen in the future also. So speaking on the first part of it, though, there are a couple examples I would give in observations. One, I bring this one out because it was the thing that was the most startling to me. A number of years ago, I saw a map of the growing zones. That is, the growing zones from agriculture that gardeners use when they plant seeds in their garden, you know, the little maps that show your zone, what grows best in your zone. And it showed the changes in the United States growing zones. I think it was it was over 20 years, from 1980 to 2000. I could see the changes, and I looked in our mountains and saw some shifts in colors and patterns and zones. But what really was startling to me was the entire state of Nebraska had moved from its historic growing zone to the next warmer growing zone, which had been occurring south of it. That really was pretty startling. The other thing I mentioned was looking at multi-year studies of what's changing and what's being observed in recent decades in forests in different parts of the world, really. One thing that we are fearing in our region is, we have over 30 different forest ecosystems in the southern Appalachian Mountains. There's high elevation spruce fir forests, there's grassy balds, heath balds, there's ridge cove forests, northern hardwood forests, lots of different forest communities. Because our mountains are so complicated, the very thing that gives us our diversity is all the different compass-facing positions of the slopes, ridges, moisture on different sides of different slopes and ridges, elevation change, all of these things, the rock layers, substrate that drives the soils. It gives us all of our diversity. Well, the one that is probably at most risk are our spruce fir forests, because they occur above 5,500 feet. So for a number of years, forest ecologists have been fearing what's going to happen. As somebody said earlier, the southern apps are a finger that sticks down into the southeastern region of the United States from the higher elevation north. So the spruce fir forests are definitely, would naturally seem to appear at risk, and they very well may be. It's easy to think of how warm species forest trees may move northward as the climate warms up and outcompete those spruce forests. With that, if such a thing happens, we will lose that whole ecosystem, perhaps, or in some places. And like the spruce fir moss spider, it's hard, it's a mouthful. That's an endangered and threatened species listed. Is it important if we lose that? Well, as Bill said, every species has a right to exist. So there could be those changes. That's one possibility, but there's also been research showing that not only do forests and trees respond to a heat index, they also respond to a water index. And I think Chelsea will show a slide about that that's pretty interesting, where some trees may move downslope, which is pretty unusual to think about. So anyway, we don't really know all these things. We're just studying them now. I also want to talk about something that's really becoming of interest to me recently, and that's, we call them vines. Technically, the botanical name for woody vines that climb up trees and extend their foliage on the surface are called lianas. And lianas are being looked at really hard for the first time. Most people sort of take them for granted as part of the forest ecosystem. But there have been some studies in different parts of the world that are showing that as CO2 increases, lianas respond faster than trees, and they're growing faster and expanding in a number of forests. Not well studied, but they're being looked at closely now. But they've observed an increase in liana biomass with decreases to the forest biomass in the forests that they're growing together, where they've been studied. This has been studied in India, in Central America, Panama, and it's pretty fascinating to me. So there's quite some interesting information about that. And lianas can actually get to be pretty old. Congaree National Park is probably one of the most studied, they've done the most study on their lianas there, and even doing, like we did old growth studies here, they did core samples and all, drilled into lianas and found that, like many old trees, they're hollow inside, but they grow on for hundreds of years. There's, they've found some that were like 200 years old, but there's some that were hollow inside, and they extrapolate those things might have been 430 years old, might even have been older than some of the old growth trees that they're growing among, which is a pretty interesting sort of thing. So my point is, we don't know much about these vines, but there's a lot of forest ecology research just beginning to see what effect they're having. And since they have a greater stem to leaf, or greater leaf to stem area than trees, their stems are very thin. They don't store much carbon dioxide, like big tree trunks, which grow much more slowly. So if they are faster growing and do cause some change, do outcompete, not outcompete, but reduce the amount of forest growth perhaps, they therefore can have the potential to change forest ecosystems. And if such forest ecosystems change, they naturally could change, have an impact on the ecosystem services they deliver to the surrounding communities, whatever those communities might be environmentally. Another point about lianas in our region were that many of them, and I was in the landscaping business for 15 years, were brought into our country from other continents for various reasons, whether it was landscaping or holding back highway banks like kudzu, oriental bittersweet for landscaping. These plants grow, they already are highly invasive and outcompete our native species because they have no natural controls. So that, coupled with the fact that they grow faster, and they often leaf out earlier and hold their leaves longer than native species, so they outcompete in that way too. That can also lead to a change in forest ecosystems. And with, again, the CO2 causing them to grow faster, that's the link to climate change, perhaps. The final thing I want to say is that with lianas, and in particular with poison ivy, which is a native species. And for those that hate poison ivy, I will point out to you that they provide one of the most nutritious berries for birds that there are. Birds really rely on them, and they spread them along edges of areas where we've disturbed them. So that's why we have poison ivy along roads, trails, brown houses, and everywhere else. In an old-growth forest, you usually see poison ivy vines that are big, and the foliage is way up there somewhere, and that's where they want to get. You don't see it so much all over the ground. You don't walk through it, and you don't catch it. So there's a little jab for promoting old-growth forests and defending poison ivy. But what has been observed, and this was observed in Duke Forest by a Duke Forest researcher, is that the effect, the toxicity of the urushiol oil in poison ivy is becoming more toxic, more powerful. And she studied this and found this to be so. And I think that the interesting connection to me with that is that back in the early 90s, for a number of years, I was a freelance nature photographer and writer, and I wrote for magazines. And I did an article on poison ivy, and among all the research I did, I decided to just call my local doctor and ask him, are you seeing more patients catching it, or anything like that? And he said, well, yes, we are. And he said, another strange thing we're noticing is that the toxicity of poison ivy seems to be getting stronger. That was in the early 90s, and this study just was in the last couple of years. So that was interesting. He was foreshadowing what we're seeing in climate change apparently is happening with lianas. So much of this is new and speculative or conjectural, but there's mounting science behind a lot of it. And all I can tell you is that we will learn more as time goes on. Thank you.
So thank you for the introduction, Susan, and thanks for the opportunity to speak here. I'm Chelsea Minniot. I'm the research project leader at Coweta Hydrologic Lab, and I work for the Forest Service, which is the other part of the partnership, that is LTER. And I've been asked to talk a little bit about mountain climate and environment and how it's changed over time. So we all know that the Southern Blue Ridge supplies quite a bit of drinking water to people in our community, but not only in our community, but for much of the Southeast. The Southern Blue Ridge ecoregion is noted here in green, and the drinking water intakes that people get their drinking water from are noted by the circles on the map. And so you can see that even though the Blue Ridge ecoregion is pretty small, about 5 million people get more than 20% of their drinking water from our forests. This is the Coweta Hydrologic Lab. The Coweta Hydrologic Lab is not a building. The lab is the area that you see behind me. It's a 5,400 acre basin. It's owned by the Forest Service. It was established in the early 30s. And starting in 1980, we partnered with the University of Georgia and were awarded the NSF LTER grant, which we continue to have until this day. If you're interested in the research that we do at Coweta, please come out. We've heard a lot about environmental education. We do about a tour a week. It doesn't matter if it's one person or if it's a group of middle schoolers or if it's the Mainspring board. We do tours, and I encourage you, if you're interested, to come out. These are some of the historical experiments that we've done. We don't have like a petri dish or a Bunsen burner to conduct our experiments. Our experimental unit is the Watershed, And so historically, we've gone out as early as the 30s. We've put different treatments on the landscape that either mimic the land use patterns or the land management actions that are available to the forest manager. And we look at the effects of those treatments or that land use change or the land cover change on water quality and quantity. As a backdrop, it helps to know what our climate is like. And so here's where I'm going to really start talking about our long-term data trends in the climate parameters that we've monitored over time. In the black and white photo above, you can see our main climate station. That's Climate Station 1, as it looked in 1934. And in the color picture is the same climate station that has been measuring the same set of parameters, sometimes with the same type of instruments over time. And this picture was shot in 2004. The climate station's still there. And we've also monitored stream chemistry across 16 watersheds since 1967. This is a topo map of the basin showing where our climate stations are located. So we have climate stations in the valley bottom all the way up to Mooney Gap at just under a mile high. And we also collect the chemical samples in our precipitation samples. So when it rains, we catch it in a bucket, we take it in the chemistry lab, and we analyze it for 13 analytes. And sulfur is one of those analytes. Bill in particular has mentioned that regulation certainly has its place. And in these data, we can certainly see how the Clean Air Act Amendment, which was passed in 1990, has reduced acid rain, or the amount of sulfate in our precipitation samples. And this translates, what the Clean Air Act Amendment was initially passed for was not to protect against, or not to regulate acid rain. It was intended to protect the chemistry of our surface waters. And so even though we've seen sulfate in our precipitation decrease, that has translated to a decrease in our sulfate concentration in our stream flow. And this is one of our low elevation watersheds, watershed 18, and you can see the sulfate concentration has declined over time. So that was a sidebar. What I want to talk about in the next 3 or 4 slides is changes in our precipitation regime. Rhett and Jack mentioned that we get quite a bit of precip at Coweta. We get over 2 meters of rainfall a year. If you look at our long-term record that we've been collecting since 1934, you can see statistically, if we get 2 meters of rainfall a year, and it's evenly distributed, we can surmise then that it rains about every 3 days. And in most seasons, we get about a week's worth of days where we get 1 inch of precip or more. A couple of patterns that I want to point out here, and I don't know if I can do it with this. Can you see that? Yeah. One pattern that I do want to point out here is the second to the bottom row here, and that is if you look at our precip over time, the amount of rain that we are getting on each day that it rains has been declining over time. That's a better way to look at it. So over time, what's plotted here is the number of rain days on the y-axis. Over time, you can see that the number of rain days has declined. But if you look at our annual total over time, the trend in our annual rainfall, we don't really see one. How many of you guys think that it's raining less now than it used to rain? Yep. How many of you guys think it's raining more? Yep. How many of you guys think it's raining both more and less? Yeah, you guys are the right ones. That's right. Because if you look at our time series and you see, if you look at the driest years, so that's this 10th and 25th percentile here, it has a negative slope over time. That means our dry years are getting drier. But if you look at the wettest years, so this upper 75% of the rainfall years has a positive slope. And that means that our wet years are getting wetter. And again, we don't see any trend in the average. So when people say climate change is really changing our average rainfall, that's not what we see here, and it's not what we see at the region scale. But we do see that dry years are getting much drier, and wet years are getting much wetter. And again, the number of days that it rains is declining over time. So summer's getting much drier, autumn is getting much wetter, and you can see that in this table here. If we look seasonally at the autumn trend over time, the 25th percentile and the 75th percentile have these positive correlations over time. So autumn is getting wetter, summer is getting drier, the number of rain days is decreasing in summer, and the rainfall per rain day is increasing in autumn. So when those autumn storms hit, they're delivering a lot more water now than they used to. And there's a theoretical basis behind this. This is my one scientist slide here. But we know from theory that when an air mass gets hotter, it can hold more water. And if you look at our humidity data over time, there's more water in our air now than there used to be. If we look at how this might affect these extremes that we're seeing, these really high rainfall events, this is a historical look at our data, not our data, but global data from 1981 to 2000. That's plotted in blue by latitude across the x-axis. And the model that they developed was the Global Precipitation Climate Project. That's in black. And so the model fits our observed data, our historic data in blue pretty well. And then they ran that model in climate scenarios, which is the red line. And so what this shows is that for mid-latitudes, we're about at 35 here, sorry, our extreme precipitation used to be about 45 millimeters per day. And in the future, under climate change scenarios, it's going to be about 55 millimeters per day. Another project, climate change project modeling, a model that tried to summarize this is the NARCAP project. It's the North American Regional Climate Change Adaptation Program. And what we see is that on the top is a map that shows the return period for precipitation greater than 4 inches. Actually, look at the bottom slide. So this is our historical data down here. For the Southern Appalachians, the return period previously was about 5 to 10 years. Every 5 to 10 years, we would get a 4-inch rain. The top map is the new map under climate change scenarios, and what we can predict is that from 2041 to 2070, the frequency of getting a 4-inch rainfall event doubles. These are some of our trends in air temperature at Coweta over time. This is one of those really just basic maximum minimum thermometer measurements. It hasn't changed. The technology and how we measure this and where we've been measuring this over time hasn't changed since 1934. Across the x-axis is time, and in the top panel is our mean annual air temperature. And so you can see a pretty pronounced increase over time in our mean annual air temperature. And if you look at the rate of that line, or the slope of the line, our air temperature is increasing by about 0.5 degrees C per decade. We also took our temperature trend record, and looked for trends in the days that were kind of hot during the growing season. And so kind of hot in the Southern Appalachian climate. During the growing season, we looked at the days that had a mean above 77 degrees Fahrenheit. And that's in this deep red color here. And the growing season days where that mean of 77 degrees Fahrenheit was exceeded, those were pretty infrequent prior to 1995. They occurred 0 times in 42 out of those 59 years. But since then, since 1995, and you can see this right along here, since then, for at least a week's worth of days in 7 of the past 11 years, it's been exceeded. And it's also exceeded 73 degrees Fahrenheit for at least a third of the growing season for 13 of the past 18 years. So, like Bob pointed out, all of Nebraska is now in a different USDA growing zone. We might be too. Someone mentioned earlier in the day, how is stream temperature changing? And I had a nice tight 15-minute slides, 15 slides to get through my 15 minutes of my time here, but I quickly altered my presentation, so I hope you don't mind. But we have long-term stream temperature data in Watershed 7 and Watershed 14, two of the watersheds that Jack spoke about this morning. And in these two watersheds, we've been recording stream temperature since 1974 and 1987. And each dot is a week. And we can see that there's a pretty tight correspondence between stream temperature and air temperature. We can explain more than 90% of the variation in stream temperature simply by using air temperature. So this has pretty big impacts if air temperature continues to increase at 0.5 degree C per decade. These are, again, climate change models that have been, actually these are data from Pete Caldwell and others. Pete's our research hydrologist at the lab. He took observations from a stream temperature network and across the 13 southern states and plotted the trend or the slope of the line and how it increases over time. And so each point is a monitoring location that has at least 10 years of data. And then the size of the dot is the trend of increasing stream temperature over time. We can also see in our long-term data where we measure stream flow that water yield, stream flow has been declining over time since 1970. And that's not because climate has been changing. Most of that decline in stream flow over time that we've seen at Coweta is because our forest is growing back. It was a pretty young forest in the 30s and in the 70s. It's now a much older forest, it's an 85-year-old forest, like a lot of forests around here. But more importantly, we've seen the species composition of our forest change over time. Once we take into account the climate change signal, which again is not driving the majority of the decline in our stream flow, if we look at the blue line plotted for two of our watersheds, watersheds 14 and 17, we can see that the blue line is our relative change in predicted stream flow that's simply due to what species are in the forest. And so stream flow can be, in some years, up to 15% less because of the species that are there. And I think this will be my last slide, but these are long-term census data for species composition over time. What's plotted on the y-axis is importance value. It's a combination of basal area and density of the tree species. And we've gone back to over 1,200 plots in the Coweta Basin over time and recorded what species are there and how big they are. And in each of these plots, you can see how the forest species composition has changed from being dominated by American chestnut in the 1930s to that really being functionally extinct in our forests now. And now what we see replacing American chestnut on all aspects and elevations in the forest is red maple. And then in certain locations and elevations and aspects, tulip poplar coming in. And these two species use quite a bit of water. This is the average growing season daily water use of the species that we have in our forest as a function of how large the trees are. And if you pluck out any one of the blue points, which are all, they all have similar xylem anatomy or wood type. If you pluck out, say, a sweet birch or a red maple, for any given diameter, they can use about 4 times the amount of water as an oak tree. I'll stop there. Thank you for your time.